Okay, good morning. Welcome back. It really looks hard from here with all of you sitting in the dark, and there's that beautiful sunshine right at the back of the room, but thank you for coming. Particular thank you also to our three speakers. When we put this section together, it looked a bit like, peer-to-peer, multimedia, things like that. We weren't quite sure what they had in common. What they have in common is that they all struggled heroically through the Belgian train strike yesterday, managed to arrive here in time. So thank you very much to all of them for that. And I'm sure the session will be fascinating. I've seen the slides as they went flying through, and it looks very interesting stuff. So our first speaker is Christos Gansidis from Microsoft Research in Cambridge, who is going to talk about peer-to-peer in general.
Thank you, Andrew. Thanks a lot for coming to my talk. Unfortunately, we have some technical problems, so I don't have a pointer. So at some point, you will hear me going into next slide and next slide, but bear with me, please. So today, I will talk about some experiences we had in building a peer-to-peer system for content distribution. And this is work that we did at Microsoft Research in Cambridge, and is joint work with various colleagues such as Pablo Rodriguez, John Miller, Dinan, and others. Can we go to the next slide, please? Okay, thank you. So, since this is a generic session of peer-to-peer, I just want to somehow give you, try to help you drill down to exactly the topics that we will discuss. In particular, one of the problems with peer-to-peer is that, as a term is very overloaded. It can refer to many things, like, for example, telephony and Skype, that we'll hear probably a little towards the end of the session, distributed computing, collaboration systems like Groove, and so on. But the area that I will most focus on today is content distribution. This is actually a very huge area, and if I had to break it down for the purpose of this talk, I would divide it into two parts. One is generic file sharing. Most of us are probably aware of systems like BitTorrent, TeamMule, Nutella, and so on and so forth. So these systems are quite popular and to some extent are really associated with the term peer-to-peer technologies. The second part relates to media streaming, and I will talk a little bit of that towards the end of my talk, but stick for the second talk, which will be exclusively on this very interesting and exciting topic. So in the media streaming world, you have technologies like Zatu, Just, PP Live, and so on. Can I go to the next slide, please? So, and the next one? Okay. Yeah, so why are we interested in content distribution? The area is hugely popular for many reasons. One of them is that it contributes to the vast majority of today's internet traffic. Depending on the report that you listen to, 40 to 70% of today's internet traffic is actually contributed by file sharing and media streaming systems. And BitTorrent in particular is, at the moment, the most popular one. The second thing that makes it very exciting, at least from my perspective, is that it gives very easy access to an amazing variety of content, right? It is very easy to find your favorite song, your favorite movie, your favorite TV show from anywhere in the planet, and get it basically very fast. So, next slide, please. Thank you. So, however, along with the excitement, we had a lot of problems dealing with these P2P systems. And one that probably comes in your mind, as most of you, I would presume, network operators, has to do with managing the P2P traffic. Right. So probably very often in the popular press, you will hear complaints from ISPs about P2P that kind of destroys their business models, or users complaining that their ISPs are trying to block their traffic and so on. So I will touch a little bit on those topics when I will tell you about the design of our system and how we dealt about these difficulties in challenging the traffic. Right. And the other, a little bit more subtle topic that has to do with management of traffic has to do with the need to find free bandwidth. So this is kind of a very challenging topic in which I will not really go unless you ask me. But the basic idea is that these networks, in order to be efficient, they depend on finding some available free bandwidth. And quite often, people have published extensively that Skype, for example, depends a lot on bandwidth from universities to provide that type of service. The second major challenge, the second major challenge in P2P comes from copyright protection, and probably all of us are aware of the record industry and the movie industry trying to somehow block P2P activities. So this is also one of the topics that we try to address in the design of our system. So before I go into the more details about our design, I want to put first a disclaimer that I'm working for Microsoft Research, and the things that we are doing here are mostly in the academic context, right? We don't really work with product groups, and the things that I will describe don't necessarily relate to any products. But I want to argue a little bit why P2P is actually very important from a Microsoft point of view, and also this kind of standard pitch I also give to our colleagues at Microsoft Corporation. So Microsoft is a big-scale software distributor. Right? Probably most of you are aware of Windows and Microsoft updates. This is a service that periodically publishes content of sizable sites to hundreds of millions of users. And this actually puts a heavy constraint on our network resources. So at the moment we provision 60 gigabps plus help from Akamai and other con-distribution networks just to support this type of service. We also do frequent release of beta versions of software, and here I put the Visual Studio example in particular. This is I mentioned Visual Studio because actually we used our system to do some public trials with Visual Studio. Maybe some of you have already tested while trying to get the latest version of Visual Studio. And also Microsoft gives a lot of free software, and obviously P2P can help us in reducing the cost for distributing this free software. Apart from the software distribution, we have MSN Video service that obviously could benefit from the use of P2P technology like the ones that may kind of see in the next presentation. And on the product side, we have various products like Folder Share Group and Live Messenger that support small-scale content distribution, mostly for collaborative purposes. Now, before I go into the kind of content distribution and peer-to-peer in particular, just want to put a small parenthesis that Microsoft historically has been very strong on, had a very strong interest in P2P, starting from XP. Peer-to-peer technologies were supporting the operating system, and that support has increased in Vista, and also if you take a look at the new .NET framework, there is more support for building peer-to-peer applications. So this is the end of kind of advertisement about Microsoft products. So what I want to present in the next is basically start with a system that we have built for peer-to-peer file distribution that we call Avalanche. So when we started it, from a research point of view, what we wanted to do is build a system that is as efficient as possible. And in order to do that, we used a technique that we'll introduce in a couple of slides, which we call network coding, to use the network resources as optimally as possible. However, as I described in a couple of slides before, this was not enough in order to have kind of a proper P2P system. And in particular, we had to take two concerns into account. The first one is that we had to guarantee a secure distribution. So I will have a slide later on that will describe what steps we took into making sure that we don't allow kind of massive copyright infringement in this type of networks, and how we can control who publishes and what is being published in this network. Moreover, we want to protect the system from malicious users, and I will also say a few words about how we actually achieved that. The second major issue in the design of the system had to do with making sure that the system is friendly to the current ecosystem of networking. So we had to take into account the requirements from various network operators and ISPs in particular. So the system had to be designed from the beginning to be cache friendly, and I will have a slide on that later on. But also, more importantly, we had to allow some form of network locality in the system. And this is an area that I will spend a little bit of more extra time towards the end. So the point that I want to make here is that, starting from optimizing the network resources, right, that was for us the main research objective, we had to actually put many extra constraints in the design of the P2P system to making sure that everybody can be happy, not only the users, but also the network operators in which that will actually carry the bulk of the traffic. So towards the end of the talk, if time permitting, I will spend some time in describing some subsequent work that we did in taking the avalanche research and extending it to support some video on demand and live streaming experiences. So the first kind of short point that I want to make is basically, an idea that we had in terms of designing an efficient peer-to-peer system that may be that's actually becoming quite popular in many other aspects of networking, and it was the main kind of research, the starting point for our research. So if you think about a P2P system, right, in a typical peer-to-peer system, you have a file that is kind of depicted there by, let's say, 3 blocks, a yellow happy face, a tree, and a half moon, right, that needs to be distributed to many machines. And then the way that it is being distributed is the machines basically take content and then they exchange content with each other. Now, the challenge is that when 2 peers exchange content with each other, they need to decide what to exchange. And they need to make a decision taking into account not only their own interests, but they need to make a decision to make sure that the system works efficiently on a global scale. This is a challenging problem. Achieving global optimality using local information is a challenging problem. And this is a problem that basically has been observed multiple times in the past. So this is some result from a study that was published in Infocom 2006 that actually documents some of these suboptimalities of current P2P systems. Right. The main idea is the following. I don't know how many of you are kind of regular users of BitTorrent, let's say, that was the focus of this study. But often what you observe is that when you start the distribution, in the beginning it takes some time, for the content to arrive, right? And then towards the end, so it takes you some time to get started, then the download progresses properly for some time, and then towards the end of the distribution, the distribution kind of stalls. Again, this is a manifestation of the problem that I described in the previous slide, that users need to make some local decisions, but to achieve a global optimal, and this is difficult. And the reason that happens is that if you focus, for example, towards the end of the download, right? By the way, here I plot the amount of time that peers spent in each percentage of the download. So towards the end of the download, what happens is that peers are trying to find what are called rare blocks. Rare blocks are blocks that have been unlucky enough and they haven't distributed properly, right? So these are kind of our main, the goal of our research was to solve this particular problem. And what we used is a technique called network coding in order to solve it. So I have tried to explain network coding in kind of very short time, in multiple times, and all of them have failed. So I will try this version, but some of you may understand it, some of you may not, so I apologize for it. So again, there is a file that we want to send, right, that we break into 3 blocks, right? And then what we do is what is called network encoding. So for those of you that are kind of more mathematically inclined, it's like linear algebra. So we treat blocks as vectors and then we do some random linear encodings of those blocks. So for those that are kind of more optical, think of it that we take the 3 pictures and then combine them in one kind of superimpose. So obviously if we take this kind of encoding thing and we combine it with something that we have already received, it is easy to see that we can actually subtract what we have received and then recover what is missing. And basically, we can do it for any piece that is missing. So basically, this is the fundamental idea of network coding. We don't send original content, we send kind of these linear encodings, right? And then this solves the problem. So again, now the idea is that by sending linear encodings, users don't need to make any decisions anymore. So if there is at least one of the blocks that I have that is of use to the system that will lead to a global optimal, the linear encoded block will also lead to that optimal, right? So we actually used this idea to distribute some beta versions of Visual Studio, right? And in that part of the system, we were kind of allowed to collect a lot of information about what happened in the network. So we collect information about all the transactions. And here we plot a similar plot as the U graph that we had before, right, for our system. Again, the x-axis is the percent of the file downloaded, and the y-axis is the amount of time that we spent in each part of the download. Here you see somehow that the flat is the curve is flat, which basically indicates that we don't have the first or the last block type of problems. Okay. What is more interesting from a content distribution point of view, and this may relate to somehow many of you that maybe want to distribute, let's say, material that is produced in your institutions to a huge audience, maybe beyond the boundaries of your network, is what the cost savings that we had in terms of distribution. So in this plot, as of my function of time, I plot the total bandwidth of the system, right? And obviously this changes because, as users come and go in the system. What is interesting to observe is the yellow line, that it is the bandwidth that we actually gave us, that we contributed as the publisher of the content, right? And you see that during the entire period of the trial, this kind of bandwidth has been stable, has been constant. So and it was actually in some cases less than 1/10 of the total capacity of the system. So this kind of indicates huge benefits for us from a publisher point of view. We didn't have to kind of provision for that amount of bandwidth. Right. And moreover, the bandwidth did not fluctuate. It was kind of, let's say, constant throughout the entire trial. We kind of, so the previous result was from a kind of preliminary study. Probably if some of you have downloaded the beta version of Visual Studio, so actually, is there anyone that has done it? Probably not, but maybe they will have another opportunity towards the end of the summer, or when is the next alpha version of Visual Studio due. So there was a client that looks like the one basically on your right, that you could use to download various beta versions of Visual Studio, like the Pro version and Team Suite and so on and so forth. So the only kind of point of this slide is to argue that basically the system worked, and it actually was able to provide quite large bandwidths, like in the order of, let's say, more than 1 megabps per second for the Visual Studio Pro users. So unfortunately, we were not allowed to collect very extensive statistics for this trial because it was kind of a public trial. But the main idea was that basically it worked, and it seemed very promising. And it was also, from our point of view, it was very cost effective. Now, so I will basically now move to the kind of second part that has to do with secure distribution. And secure distribution was extremely important for us in terms of making sure that our P2P technology is not associated with massive copyright infringement, and also to make sure that the network performs even under attacks. I will not spend a lot of time on that, but the main model that we kind of proposed was something that resembles the digital right management in Windows Media. The idea is that all publishers had to take basically some certificate from a local entity, from a certificate engine, and they had to authenticate themselves in the system. Unless they had this kind of, they were allowed to use the system to publish a particular piece of content, they wouldn't be able to publish through this kind of network. So feel free to ask me some questions about the design later on. But the basic idea is that what we want to achieve is that nobody is able to publish content without having permission. We're also able to revoke permission if there was kind of complaints from content owners. And moreover, one unique part of the system is that the clients also had to authenticate to get in the system, and we had to do that in order to block against denial of service attacks. The second part that is kind of probably more exciting from a network point of view has to do with how we dealt with some of the constraints that network operators have, and in particular, how we incorporated designs for cache friendliness and network locality. So some of you that are from Britain probably have heard about BBC's struggle with their IMP player about when they try to do the P2P release. Many of the big British ISPs complained that they would have to carry the traffic, and then they would have to carry the cost on the behalf of BBC, and they wanted actually to get money in return. So in our system, we actually try to address some of these concerns. And the first thing that we did had to do with integrating with a cache engine. So the protocol was designed from the beginning to be cache friendly. The idea is that network operators would install their kind of avalanche friendly caches, right? And they would control how the distribution of the content would go through. So either we would redirect their clients to the local cache, and also their local caches often will actually serve remote clients in order to reduce the upload costs on behalf of the clients. The thing that it was actually a little bit more interesting and practical, since it involves no kind of changes in the current infrastructure, has to do with how we try to reduce inter-ISP traffic. So in the traditional world of client-server computing, right, the flow of traffic and the corresponding flow of money was really relatively easy. So there was a server, everybody was downloading from that server, right, and then people, there were kind of monetary agreements between the ISPs of how money would exchange as a result of the bandwidth, right. In the peer-to-peer world, things have changed significantly. So imagine that, there are clients that download from the central server, but then they start exchanging traffic randomly with each other. So suddenly, providers, right, have to basically serve a lot of upload capacity for which they haven't provisioned, and for which usually comes at a very dear cost to them. And moreover, you kind of blindly increase their the traffic between ISPs to ISPs, and these are the links that traditionally are the most expensive ones. So locality is basically this idea in which we'll try to enforce connections that stay inside the same ISP. So if the peer from one ISP serves content to another peer of the same ISP, then the cost to the ISP would be small because it will not use its kind of inter-AES links. Right. So actually, we did some studies about how this type of idea would help in terms of reducing the cost. And this is actually a study that for which we have used data from the Windows and Microsoft Update service. And the point that I want to make here is that with locality, we're able to save something like more than 80% of the traffic. So, and it was relatively easy way to do so, right? In terms of basically matching the peers properly at basically the registers of our system. Moreover, one point that I kind of didn't make is that we also allowed the system that was extensible to give the users the opportunity to somehow do their peer the operators the opportunity to do the peer matchings as they liked fit. So, in total, basically, this is kind of the design, the architecture of the system. It has some seed servers, some registers, and then in the system we also put some control for a certificate authority, for content caches, and some preference to local connections. So this is kind of a visual representation of how, the system kind of looks like. So this kind of concludes the main part of my talk. I will probably spend 1 minute, if I have, on some subsequent work that we did on extending the system for video streaming and live TV. And basically the starting point of this work basically has to do with current P2P systems. So if you go out and see how those systems like BitTorrent are used, in their majority they are used to download content. And this content typically is kind of media content, right? Movies or TV series. However, if you use those systems, you will observe that often you have to wait to download the entire movie before you are able to watch it, right? It's difficult to start watching as you start downloading. And this has to do with basically the design of the system. So, and this is kind of also true in the case of live streaming, for which we'll listen in the next talk. So we'll see that basically this type of services are hugely demanding, right? But apart from live streaming is just picking up as a technology, and probably we'll see more and more of that type of systems in the future. So the question that we wanted to basically answer is, it was the following. Can we use unstructured peer-to-peer to deliver this type of video on-demand live streaming experience? And basically our approach was to starting from network coding, that the idea that I introduced a little bit earlier for efficient swarming, right? And then we built some algorithms for pseudo-sequential downloads and prefetching of data. So I will not really give you the details of what is happening, but trust my word, basically it worked quite efficiently. So these are some details about basically how it worked. So the big picture that I wanted to somehow carry over in this presentation was that it is basically easy to build a multi-purpose P2P platform that basically starts with some very basic primitives like network coding, like secure distribution to protect IP, to protect the system, to protect against malicious users. And also, we have incorporated primitives to allow IS network operators to perform traffic engineering, like topology construction, like cache friendliness, and so on. So we have used this kind of set of primitives to design various systems that use them. One of them that we spent most of our time was file sharing. This was the Avalanche system. We have done some work on software updates in the context of DeltaCast, and also video on demand and live streaming systems. So all in all, what we have learned in this study was basically, when we started, it was a few years ago, and it was, and still is the case that P2P as a technology is growing in acceptance. And in the last couple of years, we are seeing that it is getting a dent also in the corporate world. So big companies are actually considering, even actually Comcast, according to some very latest news, considering using P2P for doing content distribution. The other lesson that we learned in the design, when originally we started blindly by doing the research approach of optimizing performance, but soon we were put down to earth and we were kind of forced to think that, to take into consideration that we need to respect the entire ecosystem in the content distribution and the network operator's point of view. And one other kind of, from a research point of view, it was cute to see that network coding is a feasible and practical technology, and it is actually, in the research world, quite used today for wireless and other types of networks, apart from content distribution. And what is very exciting to see, and this actually will be more exciting in the next talk, is to see that the P2P paradigm is getting very important for video distribution and live streaming for now, and maybe video on demand in the near future. So this is all of it. So if you have any questions, I would be happy to take them if we have time. Okay. Please.
My name is Thomas Schmidt from Hamburg. Question is, you stress unstructured peer-to-peer.
Right.
Are you solely using unstructured peer-to-peer? And
so for the case of, one very interesting trend in the last years is that we see this kind of emergence between structured and unstructured. So even though in the content distribution, when we do unstructured, right, by the minute that we introduce locality, we put a little bit of structure. And one thing that I haven't showed for the video distribution, the live streaming cases, we have algorithms for kind of putting a little bit of extra structure in the network topology. It is still, we are far away from systems like, from DHT type of systems like pastry and so on, but there is some preference into peering with nodes that are close by that will give you the performance. So it's a mixed world, basically. But the starting point is unstructured.
But that leads me to the second question. the network coding approach you're using, like for redundancy in swarms or so. You're not using this together with a DHT or something.
No.
Okay.
Actually, one of the advantages of using network coding is that we don't really need to take into account how the topology looks like. No matter what the topology, by using these encoding functions, we can make the most out of it. And that kind of separates the distribution part from the content, from the topology part. So we can optimally design for topology, optimally design for distribution, and both of these type of optimizations will work together in harmony. Yeah.
Fabio Vena from Switch. Yeah. Peer-to-peer sounds to me always a little bit illegal.
That is actually very true, because when we start talking about the technology some time ago, everybody was making exactly the same comment.
How is authorization considered in peer-to-peer networks? So you mentioned the solution with certificates, but certificates
right.
are authentication. How is authorization considered?
How?
Authorization. So
authorization
I can have a certificate that means that I am this person, but I am authorized for this content or not?
No, actually you get certificate that, basically you get one certificate that tells that you are who you think who you claim to be, and you also get certificates to verify that you have the right to download a particular piece of content. So basically, you'll end up getting multiple certificates. Right? So you will have to verify through the system that you are who you are and that you have the right to download this particular content. Unless you get both of them, you will not be able to join the P2P network. Right. So, unless Andrew, if there is no other question. Okay.
Thank you. And really, all the introduction I need has been provided by Christos, so thank you very much for that. Our next speaker is Sugi Yamin from Zatu, who are in television.
Thanks, Andrew. So my name is Sugi Yamin. I'm from Zatu. Today we'll talk about how Zatu, well, what Zatu is and how Zatu works in bringing TV to the PC. Can I get a show of hands of how many people have used Zatu? Okay. Hopefully by the end of the talk, everybody would have tried Zatu. So the first part, introduction to Zatu, is more of the traditional business presentation that I usually make. And because this is supposed to be a more technical conference, I added the second part. So Zatu, for those of you who don't know, we bring live TV to the PC. All you need is a broadband connection, 500 kilobits per second, and it works on a Mac and PC and Linux. Now we have streamed about 200 to 300 million minutes of live video, which is more than the BBC iPlayers per month. And we carry more than 115 broadcast stations in 8 European countries. We don't do user-generated content like YouTube. We don't do video on demand like Hulu. And so we are strictly live. A lot of times when I make this presentation, people will ask, who cares about live? Nowadays, it's all segregated content. Watch whatever you want, whenever you want, right? Well, the fact is that we now have over 2.3 million registered users across the 8 European countries. We started, well, the company was founded in May 2005, and we started transmission in June 2006. I believe the slides are all available online. We now have entered about 28% of the broadband population in Switzerland, and we carry about 130 to 480 minutes of viewing time per user per week, which is 4 times more than YouTube. And the range there depends on which country we're looking at. The revenue model is that we put up a 5 seconds ad when we switch from one channel to another. So when the video itself is showing, we don't put any overlay on the video. We don't put any ads around the video. It's only when you switch from one channel to another, technically it takes us about 3 to 8 seconds to move you from one P2P network to the other P2P network. And in that no man's land is when we put up this 5-second ad. And so far we are seeing click-through rate on the ad of about 3 to 10%. So 3 to 10% people who see the ad will click to find out more information about the ad, which is 10 times higher than the web average. We did a user survey, mostly people aged 18 to 34. And now I think it's more, because Zatu is now more well known, it's spreading into the 35 to 45 range further. So people between 18 to 45 are the ones who use Zatu the most. And most of the time people use Zatu as we intended it, which is that we allow you to multitask while you're doing your email, filing your taxes, chatting online. You can also let Zatu run in the background. So we don't take up a lot of CPU, we don't take up a lot of bandwidth, just let it run in the background. It takes up about a quarter of your laptop screen. So, so if you compare us against other contenders in the field, we give you live TV 24/7, right? So the Major League Baseball in the U.S. gives you live TV, but usually they show you only short clips, less than 2 hours. YouTube gives you short clip archival content, just give you 24/7 but archival content. Whereas Zatu and PP Live and Live Station give you 24/7 live. The difference between us and the others who are in the 24/7 live category is that if you compare us against live TV, you have a traditional TV and you put it next to Zatu, we are about 8 to 10 seconds behind real live TV. And when you switch from one channel to another, it takes us about, like I said earlier, 5 seconds as opposed to 13 seconds or 30 seconds or 30 minutes. We give protection to the content, and like Christos said earlier, only authenticated user can access the network. The content is simulcast, it's unabridged, unaltered, and we also do geofiltering, so only people within a country can see content that we have rights to redistribute within that country. And the content is encrypted with frequently changing encryption keys, so even if the key is compromised, hopefully people will not be able to watch a whole show. And we don't allow for recording. So if you look at the Zatu player, it's very simple. There is no record, no fast forward, no rewind buttons. It makes negotiation with the broadcaster so much easier, right? You show the player there's no record, and there's no other questions of, do you allow record or not? We have launched, as I said, in 8 European countries. We are hoping to enter the US sometime this year and also parts of Asia. What else? So that was the more or less the business type of presentation. Zatu Stream itself is H.264 AAC encoded. And as Christoph said earlier, we do live streaming, which is different from file sharing and video on demand, meaning that we take content directly from satellite or from antenna, and we encode it and send it out immediately. There's no pre-recorded content that we can spend days to do network encoding or other types of H.264 multipass encoding on. It's like send it out within 2 seconds, right? The download rate is naturally limited, whereas with file sharing or video on demand, the faster you can download, the faster you can be done with the transmission. Whereas for us, because it's live, it's 500 kilobits per second max, average, but it doesn't take up gigabits at a time. Even if you have gigabits, we can't take advantage of it, right, because it's live. Data is not stored. After you finish watching Zatu, there's nothing left on your hard drive. You don't have to go clean up periodically. The buffering is only as needed, about a few seconds of data. Because it's live, recovery from packet loss or packet delay is also limited, right? If you drop a packet, you can try to do retransmission, but you can't wait forever. And because of that, upload capacity is very important to us. Upload capacity and how long a user stay on a session. If the user continue to leave a session, then we need to have backup connection ready to take over the lost users. And upload capacity is a killer. So from a network point of view, the Zatu overlay is a source-routed directed acyclic graph. It was originally 3-base n-host multicast network, and then we added shortcuts and backup links, so it becomes more like a DAG. And it's one overlay per channel. Like I say, when you switch from one channel to another, it takes us about 3 to 8 seconds to switch you. And there's one root server per channel, which is the root server that takes signal from either satellite or some other means of ingest, and plus repeater nodes, which are nodes that amplify out the bandwidth for us. So to watch a channel, first you go to the authentication server, and the authentication mechanism is our own, and it's really simple based on Kerberos. You go to the authentication server, you authenticate yourself, you get your authorization, you get a ticket. And then every time you want to switch a channel, you present your ticket to the rendezvous host, and you tell the rendezvous host which channel you want to watch. The rendezvous host sends you a list of peers, including the root and the repeater nodes who are on that channel, and then you do handshaking with those peers, and then eventually you have your connection set up with the peers. A peer selection, as Christos also explained, makes my life so much easier. You can either do it randomly, but if you do it randomly, you end up with very bad connection. Both from the peer point of view, you experience a lot of lag if you try to get content from peer who are far away, and also from the network provider's point of view, because in this case, for example, you have to traverse the backbone link 3 times in this example. So we do topology-aware peering, which means that sites peers who are within the same subnet or within the same AS get traffic from each other. And if we have a peer who can serve multiple other peers, then we put them closer to the root. And the first thing we found out, this was back in 2005, was that nets and firewalls cause a lot of problem. So in the ideal case, we'll have C sending traffic to D, D will then distribute to B and E, and then B will be able to distribute to A. But with NAT and firewalls, D and E won't be able to get traffic from C. So we end up with C having to send to B, and then B have to send to D and E. Right, so if you don't know anything about nets and firewalls, as we did back in 2005, that's the best you can do. And then, of course, we found out the STAN and other protocol that allow you to try to punch holes through nets. So now most of the net types, different net types we can deal with. The only problem is that if you have a port-restricted net, then you won't be able to share with symmetric nets. And if you're a symmetric net, then you won't be able to share with anybody. You won't be able to share with other symmetric nets. So about 20% of peers, we cannot take advantage of. So given all this problem with nets and firewalls and upload capacity, so we are sending at 500 kilobits per second for audio, video, and all the ECC data. And in Switzerland, at least on average, you have about 100 kilobits per second upload per household. So only about 20%. So given this, you want to know how helpful is the peer-to-peer network, right? So how scalable is the peer-to-peer network? So if you look at a simple back-of-the-envelope calculation, number of viewers that each channel can support depends on the root capacity, the peer out degree, how many peers a given peer can support, and the depth of the distribution tree. So if U0 is the root capacity, then and UN can be expressed as the out degree times the number of peer at the previous level, that the total peer is given by that formula. So if the out degree is less than 1, meaning that most peer can support less than one other peer, then you have limited scalability. If each peer can only support one other peer, then you're only linearly scalable. In the best case, you would like each peer to be able to support more than one peer, then you can be exponentially scalable. Unfortunately, the norm is that each peer can support less than one peer. So what does it mean that each peer can support less than one peer on average? So this is because there are free riders. Hosts behind a peer behind corporate firewall cannot transmit at all. Or peer with low upload capacity, for example, 100 kilobits per second. So that's only 20% of a single stream. Peer that are larger than, that can support more than one other peer will be our own root and repeaters, which we provision to support a large number of peers. And peers with high upload capacity, usually in university or household with fiber, which we call supernodes. And then idle peers, peers who, so this is not implemented on ZA2 yet, unlike other peer-to-peer protocols. These are peers who are not watching anything but are currently idle but are still on the network. So even though the upload capacity is small, you let them download a small substream of your stream and let them duplicate that. So we haven't implemented this, and it's not clear whether we will. So if you do a simple computation, if each peer has an out degree of 0.25 at the far column there, and your root capacity is 100 peers, then in the max, your network can only support 133 peers, 133 viewers. If your each peer can support a third of a stream, and you have 100 peers, then at the max, your network can only support 150 viewers. Right? You need out degree of 2 before you can scale. How about using idle peers? And this is partly why we haven't implemented it. If you assume normal peer can support a quarter of a stream, and then for every idle peer, you download 1/16 of a stream and send out 3 copies of it, then 80% of your network has to be idle before you can support the other 20%. And what really would help if there are a lot of supernodes, which are peers that can support multiple other peers, right? So here we show you, depending on how many percent of your network are supernodes, then this is how you can scale. So the x-axis is the multiplier on your peer-to-peer, on your root capacity. And Skype, I think, at some point has reported that about 20% of the network can be supernodes. So with that, you can scale about 2 times your root capacity. Right? So based on our observation, about 50% of the peers on the network can support less than half of your stream. 82% can support less than the full stream. And on average, a case is 0.9, but this is only the potential number. What you can actually use is much lower than that, perhaps 10 times lower than that. So what this graph shows you basically is that due to all those upload limitations, we have to put our own infrastructure in the network, which are the repeater nodes. Basically, it takes stream from the root and just simply duplicate it. And it also helps with ISPs that you can put the repeater nodes within their network so that the traffic will stay within the AS and they only need to get 1 copy from outside. So it could turn into an advantage. We now have about 500 servers operational in 15 locations across Europe, Amsterdam, Basel and Brussels, 2 in Copenhagen, Frankfurt, London, Manchester, Madrid, etc. And we are serving about 12 gigabits per second out of our own infrastructure. Channel popularity on ZA2 is zip-like, as similarly reported by other similar studies on peer-to-peer network. And which channel is popular depending on what is shown, right? So this graph shows you on different days, different channels are popular. So the same color is the same channel. And on the maximum, we have seen about 7,000 users on a single channel. For the whole network, in total, concurrently, we have about 20-some thousand users at the max. And the viewing patterns show a diurnal pattern as usual with a second peak around lunchtime. And session length, each session is watching one single channel. So on ZA2, we are seeing a session length that, on the max is about 170 minutes, and much longer than what you have, somewhat longer than what has been reported on PP Live, and much longer than what has been reported on the Telefonica IPTV network. So to summarize, P2P network can help alleviate your bandwidth requirement, but it's not sufficient to scale at the present upload capacity. Right? As the network becomes more popular and upload capacity becomes higher, in France, for example, then we can count on the P2P network carrying the bandwidth more than what it can do presently. and we continue to study performance and scalability of the Z2 network. So all the numbers I have shown you here are preliminary. They have not been published. They may be wrong. They may be corrected. Thank you.
What is the business model that you have with content provider, that is with the television channels?
What is the biggest?
The business model that you have with them.
The business model. It depends on which broadcaster. Sometimes we do revenue sharing. Sometimes, we do other types of payment. But so far, we have paid over $2 million to broadcasters for their content rights.
Okay. And in the peer-to-peer model, what happens if a peer suddenly disappears and you are receiving traffic from this peer?
Right. So we have to set up a backup connection. We have to set up backup provisioning. So when a peer disappears, we immediately switch to another one.
So there is a an interruption of the service for a few seconds, or what?
So if you look at it at the network level, yes, there's an interruption. But from what user can see, so far we have been able to mask that from the user.
Cameron Zacconi from the Belgian government. So do you think, as the actual position nowadays, most of the time in Europe, many ISPs are still having a business model based on bandwidth, maximum bandwidth per month, being uploaded or downloaded. So taking this into account, do you think that services such as Z2 may help to break this business model and open it up, or on the other side, you might die? Because people are happy to receive things and maybe receive things from another peer, but they are not, between brackets, ready to pay for somebody else watching something. Because the upstream is still within their limit and they pay for it. So do you think things will change or you will die?
Well, I may not be the right person to address this. I should get the lawyers in here. Well, I cannot give you an answer other than saying that, our current user base seems to be content that they got the TV for free and they support it, I guess, by paying for the bandwidth and by watching the ads.
My name is David Simonsen from the ID Federation in Denmark for Higher Education. I noticed that you have IP address control, access control. And in the world of ID federations, we talk about role-based access. And are you considering implementing some sort of role-based access so you would actually get to see content or go into within agreements of viewing based on who you are or what you are instead of where you sit?
Right. So that is not up to us, unfortunately. If it's up to us, then it will be easier. But it's rather an agreement or something that is forced on us by the content owners, that we have to limit distribution of content within countries.
To continue on the previous questions, I have two remarks. One point is that having a kind of delivery towards a user and not an IP, it's a real good thing, because what the web has brought to us is, there are many people who are, for instance, from a country, taking Belgium, and who lives abroad. And the way to stay in touch with their country is, for instance, just to watch the official journal on the national TV, but from their own country. And that's the reason of why radio station on the internet and live stream of radio station has been growing a lot. So this is, I think, one of the remarks which might help, because there is a very great and large potential of those people. And the second topic I wanted to know, to mention, is that IP base is one thing, but the web is full of proxy anonymizer. And this is the same problem. For instance, Canal Satellite in France has launched the fact that you can see Canal Satellite or Canal Plus in the web. They are using IP-based stuff to limit the usage, but nothing prevents to have my friend in France, which opens me just stupid VPN towards his house, and I see Canal Satellite. Just
right. So on the first point, yes, we would like to be able to distribute as widely as possible. And this being Europe, hopefully you can influence your legislator to influence the EU to, to convince Hollywood to at least let everybody have access to content within Europe. Part of it, think of it as part of human rights, that as you move between countries, as labor move between countries, people can access their homeland content. But that's up to you to talk to your legislator. On the second point, I think the leakage is probably on the same order of satellite leakage or terrestrial leakage. So if you are a subscriber of a satellite service in the UK, you may be able to take the card and go to southern Spain and still be able to watch the content. So we think that's about on the same order of magnitude.
One last question, I believe, the way I see the session chair signaling. Hans-Rudi Born-Switch in Switzerland is too interested in the cooperation with the academic world, and if yes, in what fields?
So we have multiple researchers visiting us from. So all this scalability work is done by Damien Magoni from University of Strasbourg to do performance research with us, and also we have a researcher from Leipzig doing another study with us. So I guess in academia, we'll be interested in doing research projects, or if you have students you want to send us on internships. If you have other collaboration in mind, we can talk about it afterwards. Thank you.
This conference is nothing if not variable. I told Sugi, we promised him that this was a technical conference, and he ends up discussing the EC Services Directive. So thank you for the flexibility. Okay, our final speaker is Jan Zeedorf from NEC Laboratories, who is going to talk, I think, about a slightly less favourable side of media distribution and what to do about it before it gets out of hand.
Thanks for the introduction. Although I'm very interested in peer-to-peer computing myself, and I work in a research project, this is about a somewhat different topic. I'm with NEC Laboratories Europe, and I'd like to say that this talk is also on behalf of Saverio Nicolini, who unfortunately cannot be here today. And the talk is about SPIT, and if you don't know what it is, I'll tell you about it in a minute. So let's see if this works. Okay. So here's the outline of my talk. First of all, I'd like to give you a brief introduction into voice over IP, if you're not familiar with it, and to this threat of spam over IP telephony, which we call SPIT. Then I'll discuss a bit the protection framework based on user interaction for the SPIT threat. And then I'll go into detail on some of the approaches one can think of on preventing SPIT or protecting against it. Then I'll show you some slides about a research prototype we've developed. And I'll conclude with a summary. So, first of all, voice over IP and the SPIT threat. If you're not familiar with voice over IP at all, what is it? It's basically the transmission of digitized voice over IP-based networks. Unfortunately, I cannot go into detail in the protocols involved, but there are basically two protocols used today. One is ZIP, the Session Initiation Protocol, and the other one is RTP, the Real-Time Transport Protocol. And ZIP is done for the signaling and all the managing of the sessions, and RTP is used for the transmission of then the actual media. And both are IETF protocols. You can download the RFC. They're very long RFCs with many details, but if you're interested, I encourage you to do that. We worked a bit on the session initiation protocol because when you try to prevent some threats, you want to start preventing them on the signaling layer before the session is actually being established. So SIP is basically the application layer signal protocol for any kind of multimedia session. And in particular, and this makes it different from your regular telephony that you used to do in the public switch telephony network, it supports the mobility of users and of course some other things like media parameter negotiation and session management. So just to give you a brief overview, if you're not familiar with voice over IP, it's a market that's growing very, very fast. There's been continuous growth. I'm not going to go into detail into all of these statistics. You can read them here yourself. But the main message is that there has been really, really strong growth in past years. And as you can see there on some predictions, there's going to be a lot of estimated market growth in the upcoming years for voice over IP. So this is great. I mean, this is for the economy, and for many companies it's great. But there are some problems with security, and I'll go into the next slide. Just one thing I'd like to mention here also. I mean, we talk about voice over IP here, but zip applications are not only voice over IP. So you can use it even for presence, for chatting, for IPTV, many other kinds of things. But in this talk, we focus a bit on voice over IP. So on the right side here, you can see a typical voice over IP network where you have two clients that want to communicate. Do I have a laser pointer here? Probably not. But you can see on the right side two regular voice over IP phones that try to communicate, and then two servers there. And there can be various attacks. There can be denial of service attacks, fraud attacks. Basically, all these attacks are possible because if you go to zip-based infrastructures for voice over IP, you have much more complex infrastructures than in the regular telephony networks. So your clients are much more complex, and this makes it difficult to quickly identify the cause of any problem. So what does this mean? There's obviously a decrease in security and trust. And the very basic reason for this, and I'm sure you all know this, is that voice over IP is based on IP networks, and you're familiar with the fact that IP networks are just not secure. So there's lots of attacks that can happen. There can be spoofing, sniffing. There's just a bunch mentioned here, but you can imagine any kind of things. Also malicious attacks, and of course there'll be vulnerable devices in the end. And actually, if you look on the web, you'll find lots of vulnerabilities in voice over IP devices already. I'm not going to name any vendors here, but Google yourself. So that means that if we go to voice over IP and we have zip-based infrastructures, we're going to face a lot of attacks that we don't know in the regular telephony network as much, at least. So there can be denial of service attacks, interception and modification attacks, and for all of these attacks, we've already seen quite some examples actually happening. Obviously fraud attacks, and then some social attacks like spam over IP telephony, which we call SPIT. So in summary, we need to have a detection and reaction tool to react to these security threats so we can protect our network and the users. And as it's clear from the title, this talk will focus then on some of the social attacks like spam over IP telephony. So, spam over IP telephony, what is it? Or first of all, why should we fear it? If you're not familiar, by the way, who's using voice over IP? Who's familiar with it? Okay, that's good. So, I mean, if you're a home user, you'll probably know that with voice over IP, the cost per call initiation compared to the regular telephony gets reduced dramatically, and it will be reduced dramatically in the future. I mean, as more and more voice over IP providers interconnect, you can call each other for free. So basically, this is quite important. The cost per call initiation will reduce. Then if you think about it, very low costs are actually the main reason why we have a spam problem in the email world today. I mean, there are other reasons, but I think in the spam fighting community in the email world, it's pretty much consensus. This is the main reason why we have an email spam problem. It's very low cost. So we think, and actually many other people think too, that it's reasonable to fear that if we have voice over IP telephony getting deployed largely, there will be a problem of spam over IP telephony, which we call SPIT. Now, if you're not familiar with the topic, let me tell you, it's a different thing than email spam. I think it's, if you think about it for a second, it's pretty clear. Emails get pulled from a server, I mean, unless you have a BlackBerry, but otherwise you normally pull the email. While with the voice over IP, you have a push model, meaning every time you get a call, your phone rings. And this can be in the middle of the night, this can be 10 times per minute. It gets annoying, so it's much more obtrusive. Here, I mean, there's an example. Actually, this is cut and paste what I did from one of my emails, spams I got. And imagine your telephone ringing in the middle of the night, somebody telling you this, what you see down there. It's reasonable to assume that this might happen. Unfortunately, if we look at email spam, and the difference to voice over IP spam is also that we cannot apply some of the most successful techniques for email spam directly to voice over IP. One thing that's really, really successful in the email world is content filtering. So you look at the message and filter out some words like Viagra or something else, and then detect that this is spam. For voice over IP, for real-time communication, this means you would need to do this in real time, and this is probably not feasible. So due to these differences to email spam, we need new solutions and innovative solutions. So before we go into detail and talk about some of the solutions, what you can do that people have thought of and we have thought of, I try to classify solutions with the framework. So if you think about setting up a phone call, if you're not familiar with voice over IP, just think about a regular phone call. There are different phases of a phone call. And you can actually protect against spam over IP telephony at different stages of a call. It's depicted there on the right side. So the first thing what you can do is what we call non-intrusive, where you have no interaction between either the callee or the callee. So you just look at the signaling level and do some filtering there. And I give you some examples for methods. But the main point here is you basically do you do protection mechanisms at stage 1. Sorry, maybe I should go back. Where you have no interaction with any caller. So the caller or the callee don't get interrupted or don't even feel anything of this. The next thing then is if you want to protect, you want to protect the callee, the one who gets called. So you can do then some interaction with the caller, the guy who initiated the call, to try to find out if this is a trustworthy caller, if it's a computer, and do some interaction with the caller. And also give you some examples. Then you can also then have some interaction with the callee, which we call feedback before the call. So you can ask the guy who gets called, do you want to accept this call? It's from this identity. Obviously, you can have feedback during the call and after the call. And actually, feedback after the call is quite important for statistical modules. You want to know from the user, has the last call been a bad call or not? Please tell me about it. So to give you some examples and to discuss some of the methods one can use is, well, the simple thing you can do, and this is actually quite known from the email world, is just use some black and white list. You probably know about this. If a user's on the blacklist, he's not allowed to call. If he's on the whitelist, he's automatically allowed to call. And the problem is for this, you need strong identities. It's currently standardized in the IETF. As long as you have identity spoofing, you're going to have trouble with this. I think I'll not go into any more detail on this. What you also can do if you go back to the classification I presented you on stage 1, where you have no interaction with any caller or callee, you can do some statistical modules. So this basically then boils down to pattern anomaly detection. So you have some signatures or patterns where you try to analyze, okay, does this signaling flow fall into this pattern? If it does, it might be a bad call. Problem with this is we know this from any kind of statistical methods. There are always going to be false positives and false negatives. If we have a false positive, that means that actually a legitimate call would get detected as a spit call and not get put through. This can be quite severe if there's a dangerous situation or something happens in your family and they try to call you and they get blocked because of a false positive. That's clearly not a good situation. Nevertheless, at NEC we're working on these kind of methods and try to explore them. Okay, now if you go then one step further and you want to interact with the caller and try to find out, basically, why would you want to do caller interaction? You want to do it to find out, is the caller a human or a machine? Because most probably many spit calls that we will receive in the future will be generated automatically by machines. So you want to do some tests, try to find out if this is a human or not. Again, one thing you can do is computational puzzles, which again is currently standardized by the IETF. There are some links to some drafts. So what you would do is you would give the caller a challenge, or actually the terminal of the caller an automatic challenge that it needs to solve, which should take some time. And if this gets solved successfully, the call gets put through. Now, why would you want to do this? This is actually only to fight against automatic spit generators. Or if you look at the spam world, if a machine is infected, it tries to send out millions of messages at the same time. So with this technique, the idea is to try to block this, to kind of put a threshold on the number of outgoing messages or phone calls one device can handle. Problem with this is if attackers are really clever, they come up with botnets that have huge computational power and can distribute this load, or they can even have very powerful machines that are much more powerful than the regular user terminal the user has on its desk. So there's a scalability problem. Nevertheless, it's a solution and it's being discussed. Another more obvious thing you can probably do on stage 2, where you have interaction with the caller, is to do a reverse Turing test, where you try to find out is the call being initiated by a human or machine. There are similar tests on graphical websites. If you look at the picture here, you probably know these sites. If you try to generate a user account on some pages, you get displayed some 3H5, some numbers or graphics, and then you need to type them in. And this is what's called a capture, a completely automatic public test to take computers and humans apart. That's really the term, and it's quite known, capture. And I'm just saying this because you're probably aware of video captures from the web. And there again, the idea is to try to find out, is the user who's currently trying to generate this account a human, or is it a botnet or a machine? And the assumption is that only a human can read or identify this. So with voice over IP and SPIT, we can imagine something else, and actually we've implemented it, and I'll show you in a couple of slides. You can do not video captures, but audio captures, where you, when a call gets generated, you ask the user, okay, please type in 1, 2, 3, or please type in the first letter of the current president of the United States, something like this. Again, there are issues with this, there are language problems, but it's probably a very, very clever method to try to distinguish humans and computers apart. Okay, if we go one step further and the call has actually reached the callee, because none of the methods before were applied or were not successful, there's an approach here which is called constant-based communication, where actually the callee, the person who receives the call, is asked before the call gets put through, do you want to accept calls from this identity? Again, this is based on strong identities, and it of course has problems because for every call you get from somebody, you first need to do this once, and more importantly, you are not able to receive calls from persons you don't know with this technique. So it has some limited functionality. Yeah, okay. What you can obviously do if once the call gets through, you can apply some content filtering in the back. Like I said, this is very successful in the email world, where you scan the emails which are ASCII text for some content. With real-time communications, this is much harder to do, but nevertheless, you can think of mechanisms to try to do this. And there are people working on it. I'm not going to go into detail, but I still have some time. No? Okay. And this is actually, this is then stage 5 of the framework, an example of what you can do, but I think this is quite important. At some stage, you need to have some feedback from the callee, the person who received the call. And if you have feedback from the callee after the call, you really have a method to find out was the call that got put through, was it really SPIT or not? Because in the end, only the user can decide. And so this is quite important, and we also have implemented this in a prototype and are active in the IETF to standardize this. So there can be, you can imagine a button on the user's phone. If it presses this, it signals to its provider or even to the provider of the caller, hey, the last call was an annoying SPIT call, I didn't want it. And you can imagine that such feedback mechanisms are also quite important to calibrate your statistical modules. So it's good. I still have some minutes, so I can go into detail on our research prototype that we implemented with various of these methods. It's called VoIP SEAL, which stands for Voice over IP Secure Application Layer Firewall. And it's a general voice over IP security solution, but a specific focus has been put on the SPIT threat. And you can see here on the right side, I'm sorry I don't have a laser pointer, but you can see on the right side the basic mechanism how we combine different modules at different stages. Remember, at stage 1 is where you have no interaction with either the caller or callee, so you do some statistical methods. And there we combine several statistical modules. You can see they're 1, 2 to n with a scoring system. And then based on the scoring system, we either reject or accept the call. Meaning, if the scoring tells us pretty clear, hey, there are many, many indications this is a bad call, we reject it right away. If there are no indications at all, we accept it. But if the call is, we're not sure if the scoring system that has applied all these methods is not sure if this is a SPIT call or not, it will then send the call further on to a stage 2 module where the dispatcher decides, okay, which of the stage 2 modules the call gets transferred to, and these are then basically tests to find out if this is a human or a machine, and I have some examples on the next slide. Again, there's a accept or reject mechanism there. If the test is passed, it gets accepted. If not, it gets rejected. And then further on the stages 3, 4, 5, we have some feedback processing. And you can see on the arrow there that this feedback processing is quite important to calibrate the modules in the stages in the stage 1. So the statistical modules that you use, it's quite important that you have some feedback from the user to calibrate them. So to give you an example here, I'll look a bit on the slide too so I can follow it. Let's say you have a call from a user called unknown at somewhere. So it starts a call and wants to call Bob at NEC. So the call gets sent to a server which is protected, let's assume with the VoIP-C prototype. Then this server obviously will analyze the call with some statistical modules, come up with a score, and as I've told you before, if the score is very high, the call gets rejected right away. If the score is very low, it gets accepted. But let's assume that the system is not sure. Then it will, okay, here it's displayed, it says, I'm not sure, it's a suspicious caller, we need to apply some additional tests. What happens is then, the call gets forwarded to a stage 2 module, and here I'll give you an example of one of the modules we've implemented, which is based on, in this example, I mean there can be others, but in this example it's based on the voice signal energy level. So here we assume that a regular human is kind of polite, so if the system says, hey, welcome to NEC headquarters, please wait, your call is being transferred, for example, the user will be quiet. Saverio, who actually, if Saverio, my colleague, would be here doing this presentation, he sometimes says, well, Italians, he's Italian, sometimes are not this polite. They both start at the same time talking. But the assumption is here, humans behave this way. So if I would call you and you said, hey, my name is blah, blah, I'd be quiet. And if there's a Viagra or a spit call, the machine would start automatically talking. So what we do here is we try to detect the overlap of the voice energy level, and if there's significant overlap, we block the call. I can see there are some problems with this mechanism, but in general, I think it's quite a good idea. So if the energy level of the conversation, there's a greeting that we display, and if there's an energy level of the caller at the same time, we block the call, and if it's close to 0, we accept the call. Some other things we've been implemented, we try to experiment with some of the hardware phones. I don't know if you can see this here. Up on the left is a typical voice over IP hardware phone displayed there that some of you might have on your desk, even in your company. And some of these phones actually have some nice features where you can implement stuff. So we implemented, on the left you can see here a stage 2 selection where the user can actually on his phone, I mean, he can also log onto a web page. This is displayed down below, but quite nice is that the user can actually log on his phone, go into the menu, and then select, okay, for the people who call me, I want a simple IQ test, or I want a Turing test, or I want what I just showed you, the energy level test. And on the same time, also, the user can go into a different menu and administer its black and white list. So after a call, he can go right on the phone to its list and say, okay, the last caller I want on my blacklist, or I want on my whitelist because it was my mother or something. And again, you can do all of these things on the web page. The web page login, of course, is quite nice. You can see the scoring displayed from the call. You can see there's some yellow, red from all the calls you received, and then you can click, put it on blacklist, whitelist. It's nicer. But we think it's also quite nice that the phones nowadays are capable that you can do this also on the phone. So we implemented this. Another thing we've looked at, here you have an example of a distributed network where you have some users that are outside the network which are unprotected, for example, Tom and an attacker. And on the far right you have some users like Alice and Bob who are protected from the network. That it makes sense, what we looked at is that it makes sense to have several protection devices. So we have one protection device which we call the session border controller at the gateway of the network, and we can have another one which we call the C application server, which is in the back. And as you can see, there's some communication going on between these with the red arrows. So why would you do this? Okay, why would you do this? Simple, because you have some scalability and performance problems also. So some simple attacks against malicious attacks and malformed messages and your global blacklist you would want to have on the session border controller. We also implemented a honey VoIP, but I will not go into detail here. But if you want to have some advanced functionality where you have your stage 2 or your Turing test, you you probably out of performance reason cannot do this all on the gateway. So to come back to my previous example, if the call gets blocked already on the session border controller, everything fine. If the system is not sure, it forwards the code to application server, where then there can be some advanced functionality and also some personalization. So the user can configure its own personal blacklist on this server and stuff like this. Yeah, I'm running out of time, so I will just briefly go over this here. There are some other things that we implemented. I said this already. We implemented a honeypot. We have a dispatcher module where you can select the methods that are going to be used. We did some advanced capture tests. We're working on the detection of malformed messages. This is a bit away from the SPIT threat, but voice over IP security in general. I've shown you also the customization, personalization on the phone that we implemented. And I briefly talked about the distributed rating scheme where you have a session border controller, maybe application server, and maybe even something on the phone. Yes, to conclude. Well, I think I've shown you, and only briefly, but I think it's obvious that the signaling over IP networks introduces new security threats for telephony. The reason for this is increased complexity in the terminals. Just think about it, the voice over IP terminals. Again, let me ask, who has a hard phone? Who has really a voice over IP hard phone on its desk? Okay. Okay, two. Well, but if you have a hard phone, think about it, these devices really have a complete TCP IP stack embedded in the system. So clearly, they're more complex than a regular phone. And from that follows we have new security challenges. Yeah, I've talked about spam over IP telephony, and this is expected to become a severe threat for voice over IP businesses. One thing you have to remember is that SPIT is more obtrusive than email spam. I've given you some examples. The telephone really rings. And unfortunately, today's SIP networks are not prepared for this threat. And we need innovative mechanisms against this threat because it's really different from the email threat. And I think I've pointed this out also. I've tried to show you that you can do protection against this threat at different stages of a call. I've shown you a 5-stage framework based on user interaction. And quite important, at each of these stages, you can do different methods. So there's not only one thing you can do at each of these stages. It's just a classification of mechanisms that you can use. We think, and I personally also think, that it's quite important to acknowledge that there's no single technique that will help against this threat and solve it once for all. So there's probably in the future, as again also with if you look at the antivirus world or email spam filtering, you need to combine several techniques and several protection modules. So you need a flexible solution, and that is also where it's also possible to integrate new mechanisms quickly against evolving threats. And we try to implement such a flexible solution, which we call VoIP Seal. I've given you some examples. There's a prototype where we actually also have shown some demos. One of the key features is it's modular, flexible, and extensible. And extensible is one thing I just stretched on the last paragraph, that if threats are going to evolve, it's quite important that you can extend your platform and then incorporate new protection mechanisms against new threats. Yeah, this concludes my talk. I have one last slide. I'd like to point this out. We have a conference we're organizing in Heidelberg. It's called IPTCom. It's all about voice over IP and also voice over IP security, but also about convergent services, IMS. Call for paper has already been finished, unfortunately. But if you're interested, come to Heidelberg. Bruges is a very nice city, I have to say, but Heidelberg is also very nice. Okay, this concludes my talk, and I'm happy to answer your questions.
Actually, one thing, did you somehow measure how much time it takes to go through all these methods between actually the phone can start to ring?
Yes, we did. I don't have the results here with me, but the statistical, the stage 1 mechanisms are really quick. You can analyze hundreds of calls in parallel. It's not a problem. It becomes a problem when you do the stage 2 test, where you have an answering machine or a reverse Turing test. This is actually why we came up with this distributed architecture, where you can say the simple, fast mechanisms you do at the border of the gateway, and if you're then not sure, you pass it on to a specialized server, which of course you then can have also redundant solutions or a cluster of these services. I mean, it's a it depends what kind of operator you are. If you have 20,000 users, you might need 3 or 4 of these clustered servers. It just depends.
Yeah, and one thing, do you really think that the CAPTCHA strings are really usable for VoIP? Well, especially if you consider the hard phones.
No, I mean,
typing some
maybe you got me wrong. The video captures I just gave as an example to tell you what a capture is. What we did is audio captures. So we don't have any video captures on the phone. We use audio captures where you have to solve.
Yeah, well, that a site tell you, okay, type 1, 2, 3, 4, 5. You should type it.
It's
somehow.
At least at the moment effective because most malicious software is not able to do real-time analysis of speech. In the future, I'm not sure. Maybe in 10 years, it's quite easy to program software like the enterprise has.
Yeah,
we all know that can understand. But now the state of the art is that it's quite hard to do this. I agree with you. In the future, we might think of something.
I mean, from the caller perspective, if you are calling someone, we will be very willing to hear some questions and type in the hard phone.
That's a very
keyboard,
good question.
Some answers.
That's a very good question. If you that's exactly why we implemented in that way that we first apply the stage 1 modules, which are without user interaction, and only if these are not sure, then we do the stage 2 test. So there's a high probability if you're a regular user that your call would just get through. So you only need to do this if your call is suspicious in some way. So you have a high call rate, you come from a domain that is on the blacklist, something like this. Okay?
Can I comment? I think my bank is already doing audio captures. They keep asking me difficult questions before they'll put me through to them. Sorry. There's one there.
Again, Cameron Zacconi from the Belgian government. So in a good NGN voice network, next generation network about voice, the architecture is based on SIP proxies. Mm-hmm. And within that regards, the SIP architecture itself has never to handle any media. So my question is, so is there a future in the media analysis in order to see that in fact it's somebody who wants to sell me Viagra? Because if it is the case that it's the only solutions that we have, we get back 10 years in the past with the PBX word where all the calls are getting there. Mm-hmm. And secondly, I'm a SIP expert personally on the SIP signaling. And regarding to the SIP signaling itself, there are not a lot of information compared to emails where we can scan the content, which may be relevant to identify that indeed it's a spam. Mm-hmm. And regarding to the last remark here, having an audio captcha, personally I don't believe in it because people today want to have a voice community like they had in the past. Take the call, type a number, do it as fast as possible. So if they have to listen to the question, what is the name of your mother? Yeah. They will not accept the service.
Mm-hmm. Well, you raised a bunch of issues there. Maybe I go from the back to the front. Your last point, I agree with you that it's not convenient for the user, but you said the user wants an experience just as he's used with the regular telephone network. Well, then maybe the user should not use IP networks for doing telephony. I mean, I didn't invent IP. I'm not the one who proposed to do telephony over IP. Like I said, most of the problems we have come really from the fact that we use TCP IP networks, which have no authentication. So that's the problem. Right, but the problem is, I tried to mention this in the beginning, with your regular telephone network, these calls at least cost something to the guy who does this. And with voice over IP, if you have really a flat rate, low cost model, you can assume that somebody sets up a server in a country where there is no legal agreement with and just bombs out messages. And this is what we try to protect against also. Now let me think, your second comment was... in the SIP signaling, there's not much information. Yeah, I know SIP also quite well, and I disagree because we don't only look at one call in the syntax where you already have a lot of things. You have the domain from the caller, you have the domain from the callee. I mean, for blacklisting, whitelisting, you do many things. Yeah, they can be fake, but if you know, for example, there's a zip strong identity RFC where the domain of the sender authenticates the identity. So there's some stuff you can do. But also you have to think that you don't look at one single message, but you can have stateful things. So you look at the whole session, and there you can have call frequency, you can correlate with the IP address, so you can check, does the caller, I mean the SIP package, I can spoof anything, but does this identity really belong to the IP domain? So you can do some things. At least we came up with quite a lot. And now I have forgotten your first comment. Okay. It's true, and I think also the NGN is quite a special case, because in the NGN you mostly have authenticated users. Nevertheless, you can have, as long as one gateway server is not properly working, you will have split calls from the outside. So I don't believe in the NGN being all secure and protected. Say again, what was your point? Your point was? The media, okay. I agree with you. I agree with you at that point that it's not nice. But remember that the solutions I presented to you, only some of them go back to the media. I mean, all the statistical solutions don't, and also the feedback doesn't. So the feedback I talked about is just a button where the user sends a SIP message back. I agree it's not nice from that perspective, but it's certainly a solution that's been discussed. And you also have to remember that if you don't look at the NGN, but Voice over IP today, most Voice over IP service providers I know on the internet use a session border controller, where you have correlated media and thing. So in the NGN not, but if you look at the internet world, yes. So I think that's my answer to that.
I think we should probably break for lunch and just say thank you very much to all the speakers. Thank you.